So we're finally getting into a place where we can estimate some statistics. And excuse me, we can make guesses about our population. So that's where we're leading to. It's kind of been leading up to this moment all semester. So 9.1. Let me make sure the color pen I have is right. Oh, not clear. 9.1. We are estimating population parameters. So what we're going to do for this section is kind of make an educated guess and see what falls are we're guessing a range for our parameter. So value. So at some point, we're going to say, okay, our population is X, and we find this is Y, and here's why we think it's different. For now, we're going to basically say we don't necessarily know what our population thing is, but here's our sample, and based on some statistics, we're going to say we're sure that most of our samples are going to be within this range, so it means the population's also in this range. So how we're going to do that, or what that looks like, I suppose. We have our guess, so whatever number that is. Actually, let's put guess up here. And we say guess, but it's an educated guess. We do some work to figure that out. So we're going to find a data range that's, if it's really close to our guess, our confidence level is lower because the amount of space we have to put our values in there is a lot smaller. So maybe we're like 90% confident, or we're confident that 90% of the samples are going to fall within this. If we have a bigger range, we have a higher confidence. So if you think about it, here, think about, has anyone played darts in here? Or at least familiar how darts works? You have the big, so we're throwing at our little bullseye. And if we hit out here, this is easier to hit, but we get less points. If we hit in here, that's a lot more rare to hit inside the circle, but if we do, we'll get more points. So I kind of think about that. Our confidence is lower about hitting that circle, but our guess is better. If we're on the outside, I can probably hit that. I can't always, but you're more confident of hitting that, but your guess is worse because it's a higher range, so your values aren't worth as much. Okay. Alrighty. Then we should talk about a confidence interval. So a lot of what we're doing in this chapter and beyond is talking about our confidence interval. It's an interval that we're going to create. is interval of numbers rather. Based on so we're going to use statistics. We're going to have our center number, and based on our stuff of what we'll do, we'll say, okay, here's the high value, here's the low value. Our data range is this, and that's how we're going to deal with this. Let's get the next piece out, and hopefully this will kind of come together a little bit. Our level of confidence. This is the expected proportions. This is a long definition. Of cases. Excuse me, of intervals. Wow, I can't read my own stuff. No, go away. That will contain the real parameter, which is our measurement. Is a large number of different samples is obtained. Give us our little number, and then we're going to talk about it. So these are going to be percents, which is why we're multiplying by 100. And statistics percent, that kind of goes together. Everybody's writing, so I'm gonna give you a sec before I talk about it more. Okay, so basically, if we have this interval where it, how am I trying to say this? So if we get a whole bunch of intervals, a whole bunch of samples, this is the number of samples we expect to fall within our interval. So we can't say that we're 95% certain that our real parameter is this. No, we're 95% certain that these intervals which contain the real parameter is in this space. So as our alpha decreases, our confidence increases. So our common alphas are I don't think we deal with anything but those two in this class. We can have a 0.001, which we're 99.9% confidence interval. Most of the time in here, we're going to do 0.05 or 0.01. So the 0.01 is better. It's a better confidence, but it means our interval is going to be wider. We're less exact. So for alpha equals 0.05, we get our 95% confidence ENT. If alpha equals 0.01, we're 99% confident. But again, our interval here may be smaller to where this one is going to be larger, so we have a less exact number. It's a give and take. A lot of statistics is. Okay. So for this section, we're dealing with z-scores again, and next section, we're going to get to t-scores, which is very similar. So depending on how our statement is phrased, we can read this as one of two ways. Let's look at the 95% confidence. So here's our statistic, it's in the middle, and 95% means that 95% is in the middle here. We expect 95% of our stuff to be in here. So that leaves us 5% on the outside. But we have two tails. Our graph is symmetric. So we're going to find 2.5% of cases on the high tail and 2.5 on the low tail. So this would be called a two-tailed test, and we'll get more into these later. We can have a one-tail where we just want the high numbers or just the low numbers. But our the z we would use in this case is our alpha over 2 is either plus or minus 1.96. It should be clear which one we need plus or minus. Generally, we use both in our values. We'll get there too. And our alpha over 2, so if our alpha was 0.05, .025. I'm going to give you our most common z's as we go. I said I have a picture here. Oh, that's the same picture I just drew. So we're going to use that to figure out our confidence interval. Oh, we'll get there. Okay, so we need a margin of error. So we find this by taking our z-score, which we just found up there, times sigma, which is standard deviation. And sigma p is p times 1 minus p all over n. And we're looking at proportions here. So p equals our x over our n. So it's our proportions. I did write this here. I'm going to give you this little snippet. Samples. And intervals. include our parameter. Not saying, this does not mean there is a 95% chance. No, I'm not playing music. I don't know why you're asking that. That the interval contains the parameter. Common misconception, honestly, when I was learning stats, I thought it was the second thing too. Like, oh, we're 95% certain our thing is here. No, we're 95% of all of our possible cases are going to contain this, which sounds similar, but it's not exactly the same thing. Okay. Value is going to be our Z alpha over 2. And this measures the number excuse me, of standard deviation, the sample stat can be from the mean, from the parameter. And still result in an interval that includes the parameter. Sorry, daylight savings time. Got me. Okay, so our most common ones. And if you get these down, you won't have to look up our values so often. So we have our confidence level. And this is our 1 minus our alpha. That's 100. And then we have area in each tail. And our critical value, which is our Z alpha over 2. There's our area in each tail. Okay. So if we want a 90% confidence interval, That means let me scoot this over. Alpha equals 0.1, 90%. Our area in each tail is 0.05. Our critical value is 1.645. And again, that could be plus or minus. I'm just going to leave it as positive because it works the same. I will tell you now, we don't use that one very often, but the notes listed it. So I'm like, okay, I'll add it in there just in case. More common ones. 0.05, which results in a 95% confidence interval. Split our area in half, 0.025. And our Z value was 1.96. For us, that is probably the one we're going to use the most. Finally, alpha is 0.01, which is 99%. Our area in each tail, 0.005. And our critical value is 2.575. Depending on how big a deal is we're wrong, we'll choose different ones. If we absolutely want to be sure, we're going to take the 0.01. If we don't care, you take the 0.1. Most of the time we split the difference and do the 0.05. Like I said, if you get those down, you're not going to have to look up your z-scores each time, which makes life easier. We just have it. All right, so slide 25. We have a good old Gallup poll. They were asking how much federal income tax they should have to pay. Is it too high or too low? And you can guess what most of the people said. So 45% said they consider the amount too high. We have results based on phone interviews, which isn't great anymore, but that's okay. Random sample of 1,015 adults. And we have a 95% confidence interval, maximum error of 4 percentage points. We're going to create our confidence interval. So our important data, I will throw on my slide. All right, so our proportion, our p-value is 0.451. The number in our sample was 1015. They said our alpha level was 0.05 and our margin of error was 0.04, so 4 percentage points. And actually, for this example, we're only going to need 2 bits of this data. So we want our interval. For the low value, we're going to take P minus our margin of error. For our high value, we take P plus the margin of error. So for us, 0.451 minus 0.04 to 0.451 plus 0.04, which gives me 0.491. So we're saying with a 95% confidence, we think our actual parameter is somewhere between those 2 data values. So if we were to measure everybody who falls in our category, we're gonna get some number between 41% and 49%. We get to construct confidence intervals, which looks really nasty, but isn't all that bad. Okay, so our p hat is the proportion we measure, plus or minus our z, alpha over 2, which I gave us a list of, times our p hat times 1 minus p hat all over n. And we're going to note that our margin of error, our E, is the second part of that. So the data we're going to need, we need our alpha, and we're going to use this to find our z alpha over 2. We need our n, which is number and sample. Our p hat is the number who say yes to whatever thing over the number in our sample. It's our proportion, how many people feel this way. And everything else we have. Said slide 29. Okay, we have a parent-teen cell phone survey. Woohoo. We are sampling 800 16 to 17-year-olds. So our N is 800. And we're going to see whether they've used their cell phone to text while driving. Of those surveyed, 272 have indicated they have text while driving. So we have 272 who are not liars. Obtain a 95% confidence interval with the proportion of those who text while driving. I text at stoplights, that doesn't count. All right, so let's get what we know. The number in our sample, how many teens did we talk to? 800. Our alpha was 0.05. They phrase this in the number who text while drive, so that's going to be what we're measuring. So our X in this value, in this case, is 272. Oh, excuse me. So then we know our Z alpha over 2, since we're at the 0.05 level, is going to be 1.96. And that's just the number we look up. We have them all down. Okay. We have our equation above. So let me get p hat before I do anything else. So p hat is going to be 272 over 800, which is about 0.34. It might be exactly 0.34. I did these on Saturday. I don't remember. Hey, it's exactly 0.35. I'm gonna set up my equation, but I'm gonna have to break it into two pieces. So my p hat 0.34 plus or minus my z alpha over 2, 1.96 times 0.34. 1 minus 0.34, 0.66, right? Good. All over 800. Okay. I'm going to throw this whole thing on the right side of my calculator. So I'm going to say 1.96 times the square root of 0.34 times 0.66 divided by 800. You can do this in multi-steps if you want. I'm choosing not to. 0.033. Always go out the number of decimals. Homework tells you to. My rule of thumb is one more than the original data. So my original was 0.34, so 2 decimals. I'm going to go out 3. Okay. Now we create our confidence interval. So I'm just going to say interval. And I'm going to take my 0.34 minus 0.033. And 0.34 plus 0.033. And we're fairly certain our parameter is somewhere between 31 and 37%. Okay. I'm going to pause for a moment. I want you to repeat the same thing we did, except change our alpha, which is going to change our z value. So we're going to use it with an alpha of 0.01. So things you need to do is get your list of information down, figure out what your z alpha is, z alpha over 2 rather, get that value and do the same thing. So I'm going to pause my video so there's not a lot of dead air. I'm not sure. So the data we need, the only thing that changes so far is our alpha and our z value. So our z value is now 2.575, and I just pulled that from the list I gave you earlier. So now we need to do the math. I know my p hat hasn't changed. So my p hat, 0.34. The thing that's going to change is the z value on the outside. So I get 0.34 plus or minus 2.575, 0.34 times 0.66 over 800. If I had been smart about this, I would have grabbed that one statistic before, but I forgot, but that's okay. Usually you don't do 2 of these like this. So I get 0.34 plus or minus 0.043. Then our interval. .34 minus 0.043. 297. 0.383. So comparing these two, we have the same data. Our confidence level is the only thing that's changed. You'll notice our lower confidence level has a tighter interval. The numbers are closer together. The higher confidence level has a wider interval. So you're 99% confident you can hit the bullseye, the dartboard somewhere, but you're only 95% confident you can hit it in a good spot. It's kind of the idea. Okay, one last thing I'm going to give you, and then I have an in-class activity, so I'm not going to post that on the video, is if we want a particular margin of error at a particular confidence level, how do we find our sample size? So a lot of times if we'll look at big nationwide polls, they want their confidence interval, their margin of error to be within like 0.5%, so half a percentage point. So they work backwards to figure out how many people they need to sample to get that error level. So hopefully, yeah, we want to determine population. This should be sample size, not population. Needed for a set margin of error at confidence level. So you're going to know your population parameter, or you're going to guess it. You'll know your Z value because you know your alpha, and we know what we want our error to be. So we're just going to say N equals P hat times 1 minus P hat all over, or all times rather, alpha over 2 over E squared. It's a plug and chug formula. You're going to be given most of this data. You just have to find your N. You may have to look up your Z or figure out your P, but those are both pretty easy, straightforward things to do. So if your P is unknown, we're going to use a slightly different version of the formula. 0.21 times Z alpha over 2 over E. And then round up nearest. We're always rounding up. So if you get 10.1, we're going to round up to 11. So we always go up to the next highest number. If you get exactly 10, then you're good. Anything else, you go up to the next. So let's say, I didn't write an example for this one. So let's say we want our margin of error to be really small, 0.01, which is smaller than all of our other errors so far. If we have all of this data, we're going to use our P is known equation because our P is known in this case, and solve. So number in my sample needs to be 0.34 times 0.66. My Z, which we said was 2.575. My error we want is 0.01. Whole thing squared. Four times 0.66. The inside 2.575 divided by 0.01 is going to be really big. Not that big. 257.5 whole thing squared. Seven, 9.1. So if we want a margin of error of 1%, this is how we calculate it, but we have a decimal, so we're going to round up. Whoops. We need n equals 14880 because we always round up. So we would need almost 15,000 participants to get a really small margin of error. The smaller our error, the more participants, the more subjects in our thing we need. I'm going to stop the video and then I'm going to talk about the in-class thingy. Video.